Hello, my name is Mai. I'm a researcher at Insta and going to present works at AMT Atlantique, UBS, and Leipzig on the discovery and exploitation of task hierarchy by intrinsic motivation. So let us consider a setup like this one, where we have an arm that can move around with action primitives, and it can do various effects on its environment. For instance, here it can move the blue object by reaching the object and then pushing it. The same goes for the green object. And he can also compose the positions of blue and green objects, which means that then he can use the actions that he used for each of the subtasks. So it would mean a compound action of 4 primitive actions. And because it's a DJ table, he can also use these buttons to create music, some burst sounds, or some more sustained sounds. The question is, how can he transfer his knowledge from simple tasks to more complex tasks when he doesn't know even about the dependencies and hierarchy of tasks? We showed how a robotic arm can learn its motor control to reach a simple point for a simple task like this, or to execute more complex tasks. Here it had to discover and learn what the subtasks are and which policies to use for each subtask. So to make a sustained note, we decompose it in 5 subtasks. So to move the blue and the green object, which then makes a burst sound, and then he pushes another button to make a more sustained note. Is about learning compound actions using task hierarchy. In multitask learning, we want the robot to be able to propose policies of different complexities using compound actions, as Justus Pieter named them. For us, it's sequences of primitive actions of adapted size, adapted to the complexity of the actions. And for that, we hypothesize that some tasks are related to each other and they are hierarchical. And the robot needs to discover and exploit this hierarchy. So we propose a task-oriented representation of this combination of skills and propose an algorithm to learn them, the SJMPB algorithm, socially guided intrinsic motivation with procedure battling. Our contributions is first to propose a representation that we call procedures. It's a goal-oriented representation of compound actions. We contribute to hierarchical reinforcement learning through our representation and algorithms that show that procedures enable the discovery of task hierarchy, of the dependencies and relationship between tasks. And after learning that hierarchy, the algorithm can transfer knowledge from easy tasks to complex tasks. In curriculum learning, we show that the algorithm can choose easy tasks first. And if it has access to teachers, it can also choose the most adapted teacher for each task to request help from. And more precisely, in human demonstrations and interactive learning, we show that these demonstrations bootstrap the learning when demonstrations are about policies, in the case of simple tasks, and they are more helpful when they are demonstrations of procedures or sub-goals, in the case of a highest hierarchical and complex task. We show that our algorithm can determine by itself what, when, how, and whom to imitate.